plenary speaker of this morning is Emmanuel Candès of Stanford University, and he is going to speak about the mathematics of sparsity and a few other things. Thank you very much.
All right, thank you very much. It's a great honor to be here and to address such a distinguished audience, and I have to say that it's also a bit stressful. Yesterday I was very happy to see that my colleague Mariam was awarded a Fields Medal, and Mariam certainly brings much honor to our university and our department, and I've been told that my mission in the next hour is not to bring dishonor to the same department. So we'll see how it goes. Okay, so I'm going to tell you about the mathematics of sparsity as well as a few other things. And I'd like to motivate things first, and so our first motivating example is in the area of magnetic resonance imaging. As I'm sure everybody knows, this is a wonderful modality that lets you image soft tissues within the human body. And so when you are in an MR scanner, as this little girl is about to enter, well, the scanner is actually collecting information about you and ultimately produces a picture as that seen on the right. Okay, pictures of organs. Now, the physics of magnetic resonance imaging is a bit complicated, and for example, it rests on quantum properties of matters, the fact that protons have a spin. And so I'm not going to describe this elaborate physics. Rather, I'm going to just tell you the mathematical relationship that there is between the object of interest and the data as acquired by a scan. Because you see, a scanner is not measuring proton density directly, rather it does so indirectly. And what the scanner measures is really the Fourier transform of a density of interest. And so we have a mathematical relationship between the data that the scanner collects, which is on the right, which is a Fourier transform of the image we wish to form, which is on the left. Now, at the end of a scan, what you've got is you have the data on the right, and you need to reconstruct an image. And so, of course, what you do is you invert the Fourier transform. We have a well-posed inversion. We just invert the Fourier transform, and so we can produce those wonderful images. Now, in 2004, I was approached by a team of radiologists from the University of Wisconsin, and that must have been one of the luckiest moments in my life. And these radiologists were trying to speed up acquisition times, because you see, it takes a long time to actually get a full scan. And in pediatrics especially, it's really a problem, because if you have a child, to get a high-resolution scan may take up to 2 minutes, during which a child may not take a single breath. So you have to stop respiration for 2 minutes. It's possible, but as you can imagine, it's extremely risky. So these people were interested in speeding up MR, and speeding up MR means, well, since it takes an incompressible amount of time to actually get a complete scan, to get the whole Fourier transform, speeding up means essentially measuring less, subsampling. And so this radiologist gave us a data set that looks something like this, where the Fourier transform was only sampled along radial lines going through the origin, so that in all, 98% of the Fourier samples were actually missing. Now, the reason they contacted us is that when they kind of used reconstruction algorithms to actually infer the image, which is here in this case is a well-known Logan-Shep phantom, from these highly sampled data sets, they were getting images that look like this, which are completely unsuitable for medical diagnostic. Well, we decided to run a different algorithm, and we got this. We got a perfect recovery of the input data. And the algorithm was a bit agnostic about the kind of images that we were trying to recover. It was simply doing something very simple. It was just minimizing the Euclidean norm, the sum of the Euclidean norms of the gradient of the image. That's a very simple-minded procedure. Now, my second example to motivate this talk is in the area of data analysis and motivated by this world of big data. And now what we have is array of numbers, a data matrix, if you will, and we can think about having the rows as being users and the columns as being items. And so in this case here, we have a few famous users, and then we have a few items. And so this matrix is sparsely sampled in the sense that from time to time, a user will actually rate an item. And so typically users rate very few items, And so the goal is to predict all the unseen ratings. So for example, Ingrid has not rated The Godfather. She has not yet seen it, but yet I would like to know how she's going to like it if she had seen it. Right? These kind of problems were all the rage in the United States. They are still all the rage in the US. They were made famous by the so-called Netflix challenge that you may have heard of. And it's a problem of great contemporary interest. Now, here's a surprising experiment, the second one. I've got a data matrix, which is 50 by 50. Right? And so what you see on the screen is a 5 by 5 sub-matrix. And we're going to mimic this process of, well, I'm revealing entries. And so those are the entries in the blue cells. They are being revealed. And I'm going to predict all the missing ratings. And I'm going to apply an algorithm which is exactly of the same type that what we've seen already. I'm just going to minimize the matrix norm. Right? And so it's going to guess unseen ratings. Okay? So this is my guess. And when I compare it with the ground truth, believe me, you can check it, it's completely exact. Right? So we have a second surprising phenomenon that I can guess many entries of a data matrix with no error whatsoever by minimizing some sort of matrix norm. Okay, so these two problems have something in common. Well, in both cases, we have an object of interest, which is n-dimensional. I've got information about this object in the form of linear equations. Right, so I have linear system, yk equals ak.x, but I have a very partial view of x, so I have very far fewer equations than number of unknowns. Right, so I have a highly underdetermined system, yet we've seen that it doesn't matter. Convex programming seems to return the correct answer. So what I'd like to do in the second part of this talk is to kind of explain the simplest theory I know that describes the simplest theory that kind of describes this phenomenon. So there is a bit of magic, which is we can solve underdetermined systems by convex programming techniques. And this magic rests on three things. The first is that, of course, we need that structured solution. The second is, well, we need to use convex programming, but the right convex program. And the third is a notion of incoherence that I'll try to discuss. All right, so everybody knows that underdetermined systems of equations typically have infinitely many solutions, so there's nothing I can do unless I assume some sort of structure about the vector x that is solution. And in this talk, we're going to take two types of structures. The first, what was contained in the title of my presentation, sparsity. I'm going to say that a signal or a vector is sparse, and I'm going to use the word s-sparse. If, you see, I have a long vector with n coordinates, but it's s-sparse if only s of them are non-zeros. And so what this means is that this vector x, it has lots of zero entries, and a few of them are non-zero. So I can think about a sparse vector as having s degrees of freedom. Now this is related to our first example that, I don't know if you remember the image we had, but maybe it was not sparse, but its gradient was sparse. The second concept of low complexity we're going to use is that, well, we're going to work with matrices that we wish to recover that have low rank. And so we're going to talk about rank R matrices, which have n1 rows and n2 columns. And likewise, low rank matrices have far fewer degrees of freedom than the ambient dimension suggests. In fact, if I look at the manifold of rank R matrices, it is of this dimension, and so it is much smaller than n1 times n2 if R is small. And so now I have underdetermined systems, but with some structure. And so I'd like to ask whether, well, if the degrees of freedoms is much slower than the number of unknowns, can I still solve the system? Well, a first impulse to solve this would be, well, you tell me the solution is sparse, so I'm going to try to find the sparsest solution to your system. So I'm going to try to find a vector x, which has a least number of non-zero coefficients such that y equals ax. Or likewise, if I know the solution has low rank, well, I'm going to try to find a matrix X which is consistent with the linear equations and has minimum rank. Now, this may or may not work, but in any event, as an applied person, I cannot talk about this stuff because the best algorithm I know to solve the problem on the top is exponential in n. It's basically try every subset of columns and see if it works. And the second is even worse. So it's even worse than exponential in n. So these problems are notoriously hard. They take at least exponential time in problem size. So we're going to minimize norms instead. Norms are convex, so we're going to discuss convex programs which can be solved efficiently. And so for the first problem, well, we're going to minimize the L1 norm, which is simply the sum of the absolute values. And for the second problem, we're going to minimize the sum of the singular values, and singular values of a matrix are simply the roots of the eigenvalues of X transpose X. All right, so these are two norms, and so they're convex. And so now I'm looking at a proposal which is to solve a convex program, and it's computationally tractable. In fact, for the specialist, the first one can be recast as a linear program, and the second one is always a semi-definite program. Okay, so this can be solved efficiently, and if you were at the last Congress, Professor Osher gave his lecture on new methods for solving the problem at the top very efficiently. All right, so now we have structure, we have an algorithm. Can I solve? Well, so here's a very special system which is underdetermined. And if I can have a pointer to show you, it'd be great. But okay, so we've got a matrix A, and this matrix, as you can see, is full of zeros. It has a 1 in each row. I have a vector X, which is my solution, which, as you see, is sparse. Most of its coefficients are 0, and only a few are non-zeros. And I have y equals ax. Okay, so what A is doing here, what the system is doing, and that's what I've tried to picture here, is, well, A is revealing entries of the vector X. So in particular, it's revealing the entries in those blue cells. And even if you tell me that the solution is sparse, I don't know, I just see zeros. I don't know how I could guess the value of the non-zero coefficients. So what we learn from this, of course, is that, well, if I have any hope to solve an underdetermined system, I better make sure that the rows of A's are not sparse, right? So if the rows of A are sparse, it becomes very easy for X to be in the null space of A, and so nothing can be done. So the picture you should have in mind is something like this, which is that while the signal is highly localized, or the vector is highly localized, so it's mostly zeros with bursts of information from time to time, the rows of A, if we want to have any hope to solve these underdetermined systems, cannot be localized. In fact, they must be quite the contrary. They must be global. Okay? They must be spread. So one can formalize this into a mathematical notion of incoherence. And in this talk, I'm going to discuss random underdetermined systems. And so the model we're going to assume throughout is this following, which is I have a distribution of sampling vectors, of vectors AK. And if I want to see an equation, well, they're all in a bag. And if I want to see an equation, I'm going to draw a random vector from this bag, and I'm going to show you ak.x. And if you want to see another equation, I'm going to take another sampler vector from the bag, and I'm going to show you. So for example, if in my bag I had sinusoids, I would show you Fourier coefficients about a sparse vector, perhaps at randomly selected frequencies. Okay, so this is a stochastic description of our underdetermined systems. And of course, it would not be fun if all the equations are the same. That is, when you pick a vector from the bag, they're all the same, because you'd have not m equations, but one. And so we're going to assume a condition which says that, well, the covariance of this distribution, F, the covariance of A is not singular. In other words, this sampling vector A that provides these equations, they're not lying in a lower dimensional space. Because otherwise, even if with infinite number, well, there are regions of space I will never explore, and so I'll never know what X is, even with an infinite number. Okay, so for simplicity, we're going to assume that the covariance is the identity, which implicitly normalizes these sampling vectors. But the key concept is really the concept of incoherence, and the concept of incoherence is very simply defined. It's essentially the maximum correlation between those sampling vectors and the canonical basis in which our solution is known to be sparse. Right? So I have this kind of maximum correlation, if you will, of the sampling vectors with the canonical basis. This maximal correlation, we're going to call it mu. And if mu is small, well, A, they must be spread. And if mu is high, they are localized. Right, so rather than give you a long theory about this, like let's look at two examples. The first is the case of Fourier sampling, like in our MR problem. And in this case, the sampling vectors are as globalized as it can be because they're sinusoids. And so I'm in a very incoherent case. They're not correlating well with the basis vectors. And the opposite is, of course, what you do not want to do, which is the situation in which the sampling vectors are themselves canonical elements, in case you have perfect correlations, and so the coherence is maximum. Regardless of the value of the coherent parameter, we have a result that says the following. Give me a sparse solution, consider an arbitrary S sparse vector, so a vector with S non-zero coefficients, collect measurements of the form y is equals ax star. Then, if you make sure that the number of equations is greater than the coherence times the number of degrees of freedom, which is here the number of non-zero coefficients, times the log factor, then we have this kind of miracle, if I can call it that way, which is that the solution to your L1 minimization problem, which is at the top, is completely exact. It has a unique solution, and it recovers the sparse solution exactly. So what you thought was something which was combinatorially hard is not and can be gotten by linear programming techniques. So here I have a little sort of slogan, if you will, which is that if the rows are diverse and not sparse, then the coherence is very low, as we've seen, and it's essentially equal to 1 or a few units. And I have to say that whenever you see a wiggly sign, means that there's a numerical constant. And what this says is that I can recover S sparse vectors from roughly S log n measurements under incoherence. So I can solve underdetermined systems provided that the rows are diverse and sparse and not sparse from about S log n equations. This result is tight. It cannot be improved, so you cannot by any method whatsoever hope to achieve perfect recovery with far fewer measurements. It's not possible. And I have to say that a first instance of this result was obtained with my two collaborators, Justin Romberg and Terence Tao, a while ago, where we proved that, in the case of Fourier sampling, we could achieve perfect recovery from S log n samples, and this early result jumpstart the field of compressed sensing because it has a tremendous implication for the sensing of real-world signals, which say that you can essentially sample at a low rate without information loss. Okay, but I will not discuss this in this lecture. All right, so now we're going to move to our second example. And our second example has to do with the recovery of a data matrix. And so here we have a data matrix, which is 6 by 6 of rank 2. And, well, we see that 5 rows are the same, and 1 row appears to be different. And so what this says in the context of the kind of Netflix competition I was describing before would mean that, we have 5 users, they have exactly the same preferences, and 1 is different. And now if I start to see only a few entries of a data matrix like this, well, I would get, some entries would be revealed. It is likely that I might actually complete the bottom row of the bottom part of the matrix because I might realize that, look, geez, all these users are the same. And so I might complete the bottom part. But there's no way I can complete the first vector because anything I put in the first row will maintain a rank 2 structure. And if y were 0, would maintain a rank 1 structure. So completion is not possible. Right? So what this is saying mathematically is that obviously what we cannot do is we cannot have rows that are singular. And by I mean that is I cannot have sparse subset of rows or columns that are sort of orthogonal to everything else. And again, in the context of predicting people's taste, it makes a lot of sense because if I have people who look nothing like others, there's no way I can use the experience of others to actually predict how they're going to behave. Okay, one way to say this mathematically is, again, through a notion of incoherence, which is that, well, the row space and the column space of the matrix I'm thinking to infer cannot be aligned with the coordinate axis. Because if it were aligned with the coordinate axis, I would have singular columns and rows. And so what we can do is we can define a similar notion of incoherence, which is basically the maximum correlation between the column space and the row space of your matrix and the canonical vector, right? So if the column space and the row space are somehow away from the coordinate axis, then we're going to have low coherence. And if they're somehow very aligned with the coordinate axis, then we're going to be in a high coherence situation. And we know that completion is going to be difficult. All right, so we have a second result that parallels the first, which says the following, that let's take a matrix which is n1 by n2, about which I know the values of m entries that have been selected at random. If we make sure that the number of entries is again above the coherence, which in the incoherent case is close to 1, times the number of degrees of freedom, the number of parameters a rank R matrix depends upon, times the logarithmic factor, then when I solve this minimum nuclear norm problem, it's going to guess all the missing entries, and it's going to guess it without making any error whatsoever. So what this result says is that, well, since most matrices are incoherent, we can recover most low-rank matrices from just a few entries by convex programming again. And so this result is tight up to log factors, and perhaps you can change the log squared into a log, but I cannot remove the log factor. And so it's tight both in the number of degrees of freedom and in the value of the coherence parameter. Now this result has been extended to more complicated functionals by David Gross in particular. All right, so just quickly, and these are my high school slides. So Ingrid had informed us that we should reach a broad audience. So this is for the high school students in the room. So why does it work? Why does L1 work? Well, okay, so here is a sparse vector in 2 dimensions. So this is a picture in 2 dimensions. And so I have a vector x, and one component is 0, and the other component is not 0, as you can see. Now I have one equation, so of course I know that x lies somewhere on this line. And if I were naively to minimize the L2 norm, then we know the solution. Well, that would be the point on the line with minimum L2 norm, and that's not exact, and it looks close because we're in low dimension, but in high dimension it's very far away. If, however, I minimize the L1 norm, well, these diamonds are the set of vectors that have L1 norm equal to 1. And so when I find a point on the line with minimum L1 norm, well, it's x star, and so I've got perfect recovery. Of course, I could be in an unfriendly situation where the equation is of this form, in which case the solution will not be exact. It will also be sparse, but not exact. And so, of course, the theorem the reason you oversample a bit and you have incoherence is to avoid situations like this. Okay, so what makes everything work really is that we have low complexity objects, we have sparse objects or low rank objects, and we're using norms to actually recover these objects that are extremely sharp around these low complexity objects. So in 3D here you see the L1 ball, and so I have the solution, the blue solution at the top, and so you see the L1 ball is extremely pointy at the top, and so even though the feasible set is of high dimension, it's possible for the feasible set to be tangent. And likewise, the picture on the right, well, I've got a point of interest, which is a low-rank matrix. This blue cylinder is actually a true cylinder of the nuclear ball. And again, a low-rank object is a very sharp, the nuclear ball is extremely sharp around low-rank objects. And for the same reason, the feasible set, which has considerably high dimension, can still be tangent to this thing because the ball is so sharp around the points of interest. Now, before I move into some mathematics, I think it's important to state that I'm by no means the first one to propose the use of the L1 norm. In fact, the L1 norm has been in use in applied science for a while. And to the best of my knowledge, the first mathematician who was the first to describe its extraordinary and surprising properties was Ben Logan, who was an accomplished mathematician working at the Bell Labs. And here you see Ben Logan actually getting a music award because on top of being a wonderful mathematician, he's also a world-class musician. And so I guess that really there are some people who are like larger than life, and I find it amazing. But the L1 norm has a rich history, and so here are some key players, some key people who have played with the L1 norm over the last few decades. Now, what I'd like to do in this next part is to give you a sense of why these results are true. And so we're going to do a little bit of geometry and a little bit of probability. Well, not too much, but a little bit. Okay, so here is a picture on the left that we have seen already. I have my blue point. It's at the top of the L1 ball. I've got my feasible set, which is a red line. And we know that in this case, the recovery is exact. Now, one way to express this is via the cone of descent. So the cone of descent to a norm is essentially u at x, and you're looking at the direction h that would not increase the value of the norm. Right? That's called the cone of descent. Right? And so the cone of descent, I'm sorry, I don't have a pointer. The cone of descent is this cone. And of course, the orientation of the feasible set is a null space of A. And so what we're discovering through elementary pictures is that recovery is exact if and only if the cone of descent escapes the null space. That is, if the intersection between the cone of descent and the null space reduces to 0. And when that's the case, X is solution. On the right picture, we have a different situation. This object we wish to recover is not that sparse. The cone of descent is the entire half space. And I can see that the null space does not miss the cone of descent. And what I can see is I can travel on the red line. And if I had a pointer, I could show it to you. I could travel on the red line and minimize the L1 norm by just moving inside. Right? So when the cone of descent misses the null space, I've got perfect recovery. And when it doesn't, it fails. OK. And here it fails for different reasons. All right, so on the left, the cone of descent misses a null space. We have perfect recovery. On the right, it doesn't, and so it doesn't work. Now, I'm not really working with Gaussian matrices, perhaps because they're a bit removed from applications. But for the purpose of a talk like this, it might be good to go through the simplest model in which the matrix A has IID normal 0, 1 entries. And the reason I'm going to do so is because in this case, the theory is extremely precise in its predictions. And the calculations are fairly easy. So we can sort of do online calculations, if you will. So when the entries of A are normal 0, 1, that is when the sampling vectors are themselves IID normal 0, 1, then it is obvious that the null space of A has uniform orientation. And so basically, when I say, well, what's the probability that the null space misses the cone of descent? Well, it's got to be just the volume of the cone, because it's uniform. So it's a volume calculation. Now, the volume is calculating volume of convex bodies is a subject of a field of mathematics called geometric functional analysis. And so this is an amazing field that has developed an array of techniques to actually compute volumes of convex bodies. And so we're going to use some of these tools. One thing is that we're going to have to determine the volume of a cone. So I'm going to give you a definition of a volume of a cone, which is called the statistical dimension of a cone. And it's defined as follows. Well, so you give me a cone C, the blue cone, and I'm going to immediately define its polar cone, which is the red cone. And the red cone is simply the set of directions that form a negative dot product with any directions in the blue cone. Right? So if I had a pointer, I could show you, but I don't. So, well, I've got my, every direction in the red cone has a negative dot product with every direction in the blue cone. Right? That's a polar cone. And now the statistical dimension of a cone C is simply, well, I'm going to take a Gaussian vector G, which is normally distributed with IID components 0, 1. So I'm going to call this a Gaussian vector. And the statistical dimension of a cone is simply the expected square distance between a Gaussian vector and a polar cone. Right? So you've got this distance at the top. And if somebody from the booth could bring me pointer that you could actually see, that'd be great. So we have the square distance that we see. Okay, that's okay. Well, this is Samsung's country, so I thought, well. Okay. All right, so we have this statistics. We look at the square distance, which is represented on my figure. And so I square it, I average it, and that's a dimension of the cone. Now, of course, it's a notion of a dimension, because if the cone gets reduced, the polar cone gets larger, and so the distance decreases. And so it's really a notion of a dimension. And so, in fact, it's called a dimension because if you were to take a cone, which is just a linear space of dimension d, then the statistical dimension of this cone will exactly be equal to d, hence the name. So that's our statistical dimension. And then we have these wonderful results of Gordon, who states the following. Give me a convex cone, K, and a Gaussian matrix with m rows and n columns. Then, if the number of equations you give me, which is a codimension of the null space of A, so if m is large enough, or equivalently, if the dimension of the null space of A is small enough, and if m is larger than what? Well, if we forget these terms t and 1, larger than the statistical dimension, then with very high probability, the null space of A escapes the cone. All right? Okay, so this is a very beautiful result. And for us, it says something immediate, which is that, obviously, if the number of equations, m, is greater than the statistical dimension, then I've got perfect recovery. And this connection was made by Ruderson and Vershinin. Now, to be completely honest, Gordon's lemma was not stated with a statistical dimension. It was stated for Gaussian width. But, you know, the statistical dimension is just a proxy for the Gaussian width, the squared Gaussian width. Okay, so now we're ready to do some calculations because, well, we're going to calculate the volume. So we know that we need a number of equations just above the statistical dimension. So let's compute statistical dimensions. All right, so let's do it in the case of L1. So I've got my descent cone, this blue cone. I've got my polar cone, the red cone. And in fact, it turns out, and that's the last piece of geometry we're going to use, that, well, the polar cone is simply the cone of subdifferentials. Right? So it's a cone of subgradient to the norm we're working with. Right? So it has a complete characterization as being the cone of subgradients. And it's very easy to calculate subgradients to the L1 norm. And here they are. So if I have a point x, which is non-zero, it's in S first components, and 0 everywhere else, then I am a subgradient if and only if u is equal to the sine of x when x is not 0, and it's anything less than 1 in magnitude when x is 0. Right? That's what it means to be a subgradient at x to the L1 norm. Well, now we have characterized the polar cone, so we can calculate the statistical dimension. And so the statistical dimension is, of course, the expected square distance from a Gaussian vector to the polar cone. But the polar cone, I know what it is. It's just of the form Tu, so I split the square distance into those components for which xi is 0 and those components for which xi is not 0. Okay? And, all right, so I do this. And now because ui is plus or minus 1 when xi is 0, and I can optimize the value of ui. It's very easy to calculate the optimal value of ui to compute the infimum. So I get something like this. And now I can work with this. Perhaps I can bring the inf outside of the expectation. So I get an equality. But in fact, it's not really an equality because there's a concentration phenomenon. But I'm going to write it as an equality anyway. Right? And so when I bring the infimum outside, I have an expectation of terms that are all the same. Everything simplifies. I get things that are becoming extremely simple, and I can do calculations. And so what I do, for example, by picking a good value of t is to show that, well, with 2s log n over s equations, I've got perfect recovery. Okay, so it's a very concrete, non-asymptotic result. Give me 2s log n over s Gaussian equations about an s-sparse vector. No matter what it is, I'm going to have perfect recovery by linear programming. In fact, due to a result of these 4 authors, Melungsen, Lotz, McCoy, and Trop from last year, we know that the statistical dimension produces a very sharp transition between success and failure. In particular, if the number of equations is just slightly below the statistical dimension, then convex programming succeeds with very low probability, so it fails with high probability. Whereas if the number of equations is slightly above the statistical dimension, then you have success with very high probability. And so what this describes, it describes a phase transition diagram between 2 regions, regions of failure and regions of success, which looks like this. Now let me blow up this picture. So let's focus on the picture on the left. On the x-axis, you see the number of non-zero coefficients in the unknown solution. On the right y-axis, you see the number of equations. And the yellow line that you see is the statistical dimension of the L1 cone. Now the coloring, what is the coloring? The coloring is these are computer experiments. And these computer experiments, well, if the computer fails 100% of the time, then you become a black pixel. And if it succeeds 100% of the time, you're a white pixel. And if it's half-half, you're a gray pixel. And what we can see is there are very few gray pixels. We have a very sharp transition between success and failure, completely predicted by this statistical dimension. Now, an important remark is that these phase transition diagrams about the performance of convex programming techniques in the case of Gaussian models were discovered earlier by Donohoe and Tanner, and they proved it in the case of L1 recovery asymptotically. And what's great about this work is that it uses a different area of mathematics. In fact, it uses tools in discrete geometry. So let me explain the gist of their work. And so it goes something like this. Well, I have an object that lives in n-dimensional space, and so we see the cross polytope, which is our L1 ball. And when I take measurements, well, I can think about projecting this object into lower dimensional space onto the range of A. And so these polytopes, this cross polytope, will get projected. And so the projection of a polytope is a polytope. And there are some faces of this polytope that will survive. And what I mean by survive, they will be still faces of the projected polytope. So when I look at the red faces of the polytope on the left, they are conserved through this projection because they are still faces of the projected polytope. And it's very easy to see that if your solution lies on a conserved face, then it will be recovered by L1. And if it doesn't, it will not be. And so the question becomes, well, when I take a polytope or cross polytope and I project it randomly, are low-dimensional faces being conserved? That's a question. And remarkably, there was lots of great work by Vershik and Sporishev, and by Affentranger and Schneider. And these people were motivated by the analysis of the simplex algorithms on random linear programs. And these researchers in the 80s and the 90s developed polytope angle calculations to precisely understand how many faces are actually conserved and so on. And their work itself relies on integral geometry of convexet, even earlier work from the 70s and the 60s. And what Donohoe and Tanner were able to do is they were able to continue and leverage this work, use all of this framework to actually derive these very nice phase transitions that I have presented before. Okay, so a completely different area of mathematics, also giving sharp answers to the problem. Now, I have to say that in most applications I'm familiar with, A is rarely Gaussian. The equations are rarely, the information I'm given is rarely a weighted sum of, weighted by Gaussian variables. In MR, I see Fourier coefficients. In matrix completion, I'm seeing a few entries, and it is as far as being from Gaussian equations as possible. Yet we have exactly the same result. Perhaps not as precise, but that the number of equations simply needs to be above the number of degrees of freedom times the logarithmic factor. So how can it be? Well, this is a kind of the last piece of geometry we're going to use. So we had to, in fact, people working in this field have to use other techniques to understand when minimum norm solutions actually do work. And so it's a very elementary fact that, well, X is going to be solution to the minimum norm problem if and only if there is what I'm going to call a dual certificate. For those of you in optimization, these are nothing else but the KKT conditions, really. If only if there's a vector V, which is perpendicular to the null space of A, and so it's in the row space of A, that it's a linear combination of the sampling vectors that happens to be in the polar cone. So you see the blue space here is an orthogonal complement to the null space. It goes through the polar cone, which is a cone of subdifferentials, and therefore we've got perfect recovery in this case. Of course, in this case, the row space of A escapes the polar cone. I cannot construct such a dual certificate, and that tells me that X cannot be solution to my optimization problem. Now, just to kind of give you a sense of the mathematics that go into this non-Gaussian world, okay, so we can have, we need to build a dual certificate, and so I need to find a vector V, which is in the span of the sampling vectors A, and is a subgradient, and so we've seen the definition of the subgradient. It matches a sign where the solution is not 0, and it's less than 1 in magnitude everywhere else. So in the case of MR, so when I actually see random Fourier coefficients, well, what I need to do is I need to build a linear combination of the sinusoids. So I need to build a trigonometric polynomial which is sparse. It only uses those frequencies that have been measured. And this sparse trigonometric polynomial needs to do two things. It needs to interpolate the sign of X, which is shown on the right, and everywhere else it needs to be less than 1 in magnitude. So it needs to be in between plus and minus 1. Okay, so that's becoming analysis. And so as you can see, it's very different from the kind of volume calculations we've seen before. And so here is one way to try to say, well, what I'm claiming, what the first result I've shown you says is that, well, if the number of equations is S log n, then there is such a thing. All right, so how do we go about establishing things like this? So this is my dual certificate, rewritten in matrix notations. V is in the row space of A. If and only if the projection of V onto the support of X is equal to the sign, and the projection of support has magnitude less than 1. So one way to actually do this is to say, well, let's try to exhibit a candidate certificate. Let's try to construct such a V. And so I have two affine equations. The projection must match the sign, and V is in the row space of A. And so the proposal is to actually find a vector V, or construct a vector V, which has minimum L2 norm and obeys two of the three conditions I know, the two affine conditions. And of course, the intuition behind building such a vector V is to say, well, because V has minimum norm, well, we hope that off support is going to be small. That's reason number one. And reason number two is, well, it's a least squares problem, so I have an explicit solution, which is shown on the right. Now I have a random object. It's very complicated, right? So if I look at the matrix inverse, inside the inverse, I've got a time limiting operation and a frequency limiting operation. And so I have this very random object, and I need to control its norm. And that's not easy. And so the kind of, this is the solution, right? On the previous example, that's the candidate certificate. It interpolates the sign. It's in the row space by construction. It's less than plus and minus 1 everywhere else. So we succeed. So numerically we can check, but obviously you need to prove theorems. So, well, we're going to have to go through proofs. And so the proofs are complicated. They're going to use tools from combinatorics, tools from geometric functional analysis, like decoupling techniques and non-commutative Khinchin's inequalities and stuff like this. And so it's a very different world. What I want to say, though, is that if I were to deploy this program in the Gaussian case, I would get very sharp answers already, which means that, you know, this candidate certificate is not such a bad thing. All right. So in the last 10 minutes or 15 minutes, What I'd like to do is I'd like to close this lecture by showing you some immediate applications and some perhaps broader implications of the stuff we've just discussed. So I'd like to return to medical imaging, and now people need to focus attention on the middle screen because this is where you'll see images better. And so a lot of medical teams have actually understood that the opportunities offered by subsampling followed by optimization. And I'm going to highlight the work. Many people do this now, and if you go to MR conferences, a lot of it is about this stuff. But I'm going to highlight the work of Lustig, Pauli, and Vasanawala that I know best. So what these three researchers have shown is that you could get exquisite images going 8 times faster than conventionally. And so here you see a picture of a 6-year-old that has been accelerated 8 times by subsampling followed by convex programming, a technique I will from now on refer to as compressed sensing. And so whereas it takes 2 minutes to acquire its scan, because you use these techniques, now it uses only 15 seconds. And as you can see, it's still extremely rich in details. All right, so here's another picture. Now it's of a 1-year-old female with liver lesions, again accelerated 8 times. The image on the left is actually what you get conventionally, okay, conventionally. The image on the right is what you get by this compressed sensing technique, subsampling followed by convex recovery. And so on the right, you see where you see my little arrows. You see white spots, which are lesions, which are barely visible on the left, are quite visible on the right, which is what those doctors care about. All right, and so it's quite remarkable that we can see them, even though the picture on the right takes 8 times less to make than the picture on the left. Now we see a picture now on a 6-year-old boy. Okay, this is it's his abdomen, and so I'm gonna blow it up, and so you see veins and ducts and all kinds of stuff that are barely visible on the picture on the left, which still takes 8x to acquire. And so this is the reason why these techniques are extremely used now, and so they may have a big impact in pediatrics. And rather than giving you a long story, I'm going to give you a short story, and it's an anecdote, a true story. So there was a little boy, and he had received portions of a liver, but his medical tests were extremely alarming. And so the doctors needed to have a very high-resolution scan to see what was wrong. But high-resolution scan, as I mentioned earlier, takes 2 minutes, 2 minutes during which the boy cannot breathe even once. So you'd have to stop the respiration, so deprive the brain from oxygen for 2 minutes, and you can imagine that at the end of the 2 minutes, the liver may be the least of your worries. So this boy came to Stanford Hospital. The doctor there put the scan in a compressed sensing mode, going for a 15-second scan by these techniques that we've talked about. The scanner produced the pictures that a bit like the one you see on the right. The doctor saw that there were 2 ducts that were blocked. They performed surgery, and now everything is well. So this is our first application in medical imaging. Our second application, still in imaging, which is less of an application, it's more like where these ideas can take us, has to do with phase retrieval. So phase retrieval is a very old problem, and it has to do with the fact that light is a wave, and by virtue of being a wave, it has an intensity and a phase. The problem is that detectors can measure intensity, but they cannot measure phase. And so when I have a light field, X, which goes into an optical system, and I have a camera in the end, or whatever, or my eye, I will not see the phase. And so what the detector can measure, assuming that we have linear optics, so the light field has been transformed linearly by a matrix A, assuming we have linear optics, what the detector will see is not the wave field, it will see the squared of the wave field. So instead of seeing AX, it will see the squared modulus of AX. In other words, you're going to have quadratic equations. All right? And this is, as I said, a very important problem because, well, it's a problem that has puzzled mathematicians and physicists alike for about 100 years. And in fact, phase retrieval is at the heart of X-ray crystallography, which is a technique whereby one can determine the atomic structure of a crystal by looking at the diffraction pattern when it's illuminated by an X-ray and try to infer the periodic structure. It's a very old problem. Now, for those of you, I'm sure many of you have been in yesterday's talk, solving quadratic equations. So phase retrieval is about solving quadratic equations, and it's extremely hard. I mean, I don't know of any good algorithms to solve quadratic equations. It's very, very hard problems. Now, of course, we need to form images, and so people have developed solutions. They're a bit ad hoc. Sometimes they work well, and sometimes they don't, and what's for sure is that there's very little theory about what these methods do. So these are quadratic equations, so you might wonder, what does this have to do with all this talk, which is about linear equations? Well, what we can do is we can convert these quadratic equations into linear equations. And so the short message is that solving the phase retrieval problem is a matrix completion problem. In fact, it's a rank 1 completion problem. So let me explain this. When I've got a dot product, the squared dot product, ak.x squared, well, I can think of it as, well, I can rewrite it as a trace of a rank 1 matrix, which is ak star, and a rank 1 matrix, which is xx star. And so if I call the matrix xx star capital X, it is the trace of a rank 1 matrix times capital X. So it's a linear equation about capital X. So by lifting the problem in the space of matrices, things that were quadratic become linear. And now the phase retrieval problem is literally a rank 1 completion problem, because what is it? It says, well, what you have to do, Emmanuel, is you have to find a matrix X which is compatible with a linear measurement, but it's xx star. So it has to be positive semi-definite, and it has to have rank 1. So it's a matrix completion problem. I said, well, I can't solve this. It's still as hard as the original one because the rank constraint, I can't deal with it. So let's drop it. It's too difficult. So let's take a proxy for this. Let's minimize the nuclear norm, but because X is positive semi-definite, the nuclear norm is simply the trace. So let's minimize the trace subject to the same constraints. All right? And this has a flavor of some of the stuff you heard yesterday in a completely different context. For example, it's, of course, extremely connected to the relaxation of max cut by Goemans and Williamson. It's a slightly different relaxation, but what's amazing is that these relaxations were not considered in imaging problems. Despite these connections, we're going to see a result which is very different from what you've heard yesterday's in Professor Aurora's lecture and Professor Cott's lecture. You'll see we have a sort of a different result. So we're going to solve the problem on the right. It's a convex program. We can solve it at least. It's polynomial time. There are many polynomial times algorithms and some good algorithms to do it practically. Okay, so we have the combinatorial optimization problem on the left in its convex relaxation on the right. And the surprise is something like this. It says, well, give me randomized quadratic equations, and here I have a model for the random sampling vectors, which are their independent on the sphere, but there are many versions of these results with other sampling distributions. Basically, give me random quadratic equations, and give me a constant times n of them, so proportional to the number of unknowns. Then the relaxation we have on the right has a wonderful property, and that property is very simple, that when I look at the feasible set, that is a set of matrices that obeys the linear constraints and are positive semi-definite, well, there are not many. They're just one, and it's xx star. So when I solve a convex feasibility problem, I'm guaranteed to find xx star under the stated assumption, obviously. And now I factorize it, and I have x to global sign. So I've solved the phase retrieval problem. Okay, so what this is saying is that this theory, this rank matrix completion theory says that, well, in some cases, we can solve like very hard problems that have to do with solving quadratic equations. Exactly. Okay, my last example is more fun, and this is my last example and the last 3 minutes. It's more fun, so this is motivated by problems, modern problems in data analysis, where I'm seeking to reduce dimensions. So I have a data matrix Y, and this data matrix is a sum of a low-rank matrix and a sparse matrix, but I do not get to see the low-rank component, and I do not get to see the sparse component. I just get to see their sum, Y. And as you can imagine, what I'm going to ask you to do is to find L and to find S. Perform this blind deconvolution. And why do we want to do this? Well, perhaps the columns of this data matrix, which is represented on the right, well, they are points living in low-dimensional space. But because data collection is never perfect, they've been corrupted. Maybe sensors have failed or something. Right? So I have corruptions, which is modeled by this sparse matrix. Right? So S will be non-zero at the locations where these entries have been corrupted. So I want to perform dimensionality reduction. I want to find a low-dimensional structure. But whenever I'm looking at an entry of the matrix, I don't know whether it's been corrupted or not. All I see is this. And yet, I want to find a low-rank structure. So I want to separate L and S. So the question is, well, can we recover L and S accurately? And if we could, that'd be great, because what this says is that we could, do principal component in the face of severe corruptions. But it looks impossible because it's underdetermined again. All right, so I've got these problems, this blind deconvolution problem. I observe the sum of a low rank and sparse matrix, and I know nothing about the low rank component. The rank is unknown. The sparsity is unknown. I don't know how many entries have been corrupted. I don't know where they are. The magnitude of the corruption, there's nothing I know about this. And, well, it's a talk about convex programming techniques, so we're going to go at it by a convex program. And all what we're going to do is we're going to minimize, we're going to try to find a decomposition, L and S, that minimizes this norm, this mixed norm, where I'm going to minimize the nuclear norm of the low-rank component and the one norm of the sparse component, the one norm of S being simply the sum of absolute values. All right. And, well, this is the last thing, which is that if you give me a low-rank matrix which is incoherent and you corrupt it in many, many places, and how many places you have the right to corrupt positive fractions of entries, I solve this optimization program, which is a convex program, with a value of lambda, which is 1 over square root of the dimension. And so the result is that what this algorithm will spit out, it will spit out a low-rank matrix, which is exactly the low-rank matrix you're looking for, and it spits out a sparse matrix, which is exactly the sparse matrix you're looking for. So you have perfect demixing, right? So it doesn't matter what the magnitudes of L and S are. There's no tuning parameter. It just finds out the corruption on its own. Okay, so some geometry has something to do like this. Okay, so 2 minutes of video time, and then we're done. So I have a few movies, if you allow me. And so in these movies, because movies show well, so I'm going to think about them as data matrices where the horizontal axis, so the columns will index time, and the rows will index space, so that a column of my matrix is essentially a frame of this video sequence. Now when I take a video sequence, which is on the left, and I decompose it as a low-rank plus sparse component, well, the low-rank component is the stuff that is correlated, so it's going to be something that looks at background, and the sparse component is the foreground. And so just by performing this L plus S decomposition, while you separate background from foreground, which is an important problem in computer vision, so you can look at the low-rank components. So these are a video, so the columns are the low-rank component. You get background, and so you have automatic background from foreground separation, automatically. Okay, going back to medical imaging, now we're exploring the potential of this L plus S model of modeling dynamic video sequences in MR as a static component, which you can think about as a low-rank component, and a sparse innovation on top of this static component, which is our vector S. And so we're going to try to recover and get high-quality dynamic MR video sequences by using these techniques, by minimizing, finding the most low-rank plus sparse explanation of data collected by a scan. All right, so first of all, visually, people like this because, well, it does automatic background separation, so doctors want to see blood flow, which will show, of course, in the sparse component. Right, so this is, by just looking at the sparse component, you subtract the background, and so you can see, you can follow the blood flow through the veins. But I guess the thing, and by the way, this is really joint work, and when I say it's joint work, it's really the work of my colleagues, Aug14Thu and Daniel Sodikson, who are radiologists at NYU. Now, but what we really like about this is that this kind of L plus S model, put in compressive mode, is very useful for actually getting high quality images and videos. So on the left, what you see is, and I don't know why it should replay, but on the left you see what is done conventionally, and then on the right you see this L plus S decomposition with a bit of engineering tricks, like a bit of motion compensation. And so what you see is you get much cleaner and sharper images than what you see conventionally on the left. And so we can look at frames and look at these things frame by frame. And so on the left you see what people do conventionally, and on the right you see like the potential of these techniques for imaging. Okay, so this is a second video of similar flavor where you use these ideas of low rankness and sparsity to actually get the best image quality or video quality we can hope for. Okay, and so again, freezing on this, on the left you have what's done conventionally, and on the right you see what these kind of convex programming techniques can do. Well, my time is up. So there are many things I've not talked about. This is a huge field, so you have to make some choices. And I've not talked about deterministic results. I've not talked about what happens when you have approximate sparsity or approximate low rank. I've not said anything about noise, which is extremely important because in every application we're going to have noisy data. I've not talked about computational issues. I've not talked about lots of applications. There's very little I've done. What I hope, though, that I have done is convey a sense that this is a field of science and mathematics that brings together people from the math world, people from the medical world, people from the engineering world, people from the science world. And I think what's great for me to be working in this field is you go to conferences and you could have literally a circuit designer sitting next to a mathematician, and that rarely happens otherwise. So it's a great field to be in, and with lots of very exciting interactions between all walks of life. And personally, I've been very fortunate in my little ecosystem to work with incredible people, mathematicians and statisticians, of course, but also scientists, engineers, computer scientists, doctors. And so I'd like to thank them all for what they've given me and you for your attention. Thank you.
Thank you, Emmanuel, for a beautiful talk. We have time for one or two quick questions. Okay, if there are no questions, let us thank Emmanuel, and I believe we have a present for our speaker. Thank you.